So, so let's continue then. So we're going to talk about mostly today about hydrogen. So when we started to talk about quantum mechanics, and we were discussing experiments which classical physics could not explain. So this quantization of energy levels of hydrogen-like atoms, that was one of the problems quantum mechanics could not explain. So then after a while, when you introduce photons and de Broglie wavelengths, and then you introduce Bohr model of atom, but this Bohr model still is not based on solution of a quantum mechanical problem. So last time it took a lot of efforts for us to realize that we can introduce angular momentum in quantum mechanics, and it would be normal angular momentum definition, but you put operators. And then you have to select operators which commute between themselves, and if they commute, they can share common set of eigenfunctions. And then apparently operator L square commute with everything, and another operator is either LZ or LX or LY, but you cannot pick more than these two. So you can pick LZ and LX because they don't commute and so on. So this would be a minimum set of operators which commute. So then you can pick a wave function, and this would be a spherical harmonic, which have a certain angular momentum and certain z component of your angular momentum. So L square, this is the length of the angular momentum squared. So and this would be something like h bar square L plus 1. So I'm writing this eigenvalue, eigenfunction. And the same function would be eigenfunction of LZ operator with the value h bar m. And the spherical harmonics are not very simple functions. We could write maybe 1, 2, 3 initial wave functions. And then mostly you're going to use the properties like this rather than direct expression for the spherical wave function. But these functions are not too complicated, I would say, and they're a function of angles. So for example, the phi dependence is relatively simple, but the dependence on angle theta would be a little bit more challenging than this. So this was one of the achievements from the last time. Now, for this state, the m is a magnetic quantum number, will be confined by this L. So it's going to change from minus L to plus L with step 1. So you have 2L plus 1 different values for this M. And last time we discussed, because we were talking about orbital motion. So when angle phi increases by 2 pi by 360 degrees, you basically will come to the same point. And your wave function should not change because it's a wave function at the same point. That means your m and L should be integer numbers. This is true for orbital angular momentum, but it's not true for spin, which we did not really talk about yet. What's going to be true for everything, that this 2L plus 1 must be integer because the step is always 1, and we know this because of this rising lowering operators, L plus, L minus. So basically this one must be integer. So technically speaking, L could be integer and half integer. but because you're talking about angular momentum, angular momentum, then L cannot be half integer. For spin, for internal angular momentum, we don't have this restriction. That's nice. So then that was one of the achievements for us. The second achievement was the operator Laplacian or momentum square in 3D. So if you have 3D motion, and when you're talking about hydrogen atom, yeah, it's a motion in 3D. Then you have to take into account all 3 degrees of freedom, and in terms of if I plug the expression for P operator, then I'm gonna get something like this. So life is getting very complicated when you move to 3D. So this operator is well known, it's called Laplacian. It's a gradient square, basically. So this is a normal triangle, kind of a symbol to express this Laplacian. But because we want to work in spherical coordinates, I have to rewrite it in spherical coordinates. And then in spherical coordinates, this operator p square would be minus h bar squared, the radial part of Laplacian and angular part. And the angular part of Laplacian comes with 1 over r squared. So if you open any book and try to find how your Laplacian looks in 3D in spherical coordinates, you'll find out something like this. So the radial part is second derivatives over r plus 2 over r d over dr. And the angular part, I can write it if you want, but actually it will be more convenient for me to express this angular part through the operator L squared. And I did not prove it to you. And I did not, of course, calculate this L square operator. I just want to report you some the result for this. So then this angular part would be equal to negative operator L square over h bar square. So basically, I would like to cancel this negative minus h bar square. So this is something I don't prove to you. I'm just asking you to maybe to check it yourself, or just trust me for a while, or just say if this is true, then this is, yeah. And I can write it, of course. It's not a big deal. I believe it's something like 1 over sine theta d over d theta from sine theta d over d theta, and then plus 1 over sine square theta second derivatives over phi, something like this. So it's nice too. Not that simple. So this was our second achievement from the last class. And finally, I would like to expand this set of operators which commute. So if you have spherical symmetry, spherical symmetry, with spherical symmetry, your energy, the Hamiltonian, is not going to change under rotation. So if you commute with this operator L, any component, x, y, or z, you're going to get 0. It's going to be 0 with Lx, Ly, LZ, and of course it's going to be 0 with L square. So this only happens if your system has some spherical symmetry. That means if you rotate your system and measure energy, or you measure energy and rotate, it's not going to be different energy, it's going to be the same energy. You have certain spherical symmetry. So let's say you have a proton, electron, and you have certain energy of interaction. What if you rotate your atom? The energy of interaction would be the same. So your Hamiltonian, which represents the energy, does not change under rotation. And in principle, we don't have time for this. The symmetry plays a very, very important role in quantum mechanics. Now we are talking about symmetry under rotation, but there are many other symmetries. So a small conclusion coming out of this, then I can expand the set of operators which commute and which can share eigen functions. So that means because my Hamiltonian commute with LZ and L square, I can say my operator H applying to some wave function, but the same function can be eigen function of operator L square and the same function can be eigenfunction of operator LZ. So then this function can have some labels. L, because it's a eigenfunction of L squared with the value L. M, and maybe some energy, whatever. Yeah. So I can do this only because these operators commute. For example, I cannot include Lx to this because Lx doesn't commute with Lz. Lx would commute with L squared and H, no problem, but not with Lz. I cannot include operators like P or P square. P square would not commute with Hamiltonian. So usually you try to create a set of these operators which commute as large as possible. Okay, so then we agree that my function already has certain angular momentum and it has certain z component of angular momentum. So when this operator L square will be acting on my function, I can replace the action of this operator with just a number. So it will make my life really easy, or as much as possible. And I don't really have to care about this angular part of the Laplacian in the kinetic energy. So we're gonna search solution in this form. Some radial function and angular function. So the second part is responsible for distribution in this angular space. So you have a probability or amplitude of probability to find your particle at different angles. And this would be characterized by L and M. L is the maximum projection and M is the LZ component of angular momentum. And let's assume that we know the spherical function. And R function will give me the radial distribution. distribution. So our goal basically to find this radial distribution and to find possible energies. And I would probably just focus on the energies because I would like to get the spectrum of hydrogen. So what we did last time as well, we tried to write the Schrodinger equation. So kinetic energy minus plus potential energy applied to my wave function. So this is a Hamiltonian, yeah? Must be equal E psi. Maybe some operators, yeah? But for P square, I want to introduce this radial part of Laplacian and angular momentum square. So it's going to be minus h bar square over 2m second derivatives over r plus 2 over r first derivatives. This is only the radial part of this p, so this one, yeah. And for the angular part, when you act with operator L square on your psi, you can replace it with a number. So then you have this operator L square, which is the angular part over 2mr square psi. But you don't have to worry about this L square. It's just a number, because once you act on this, and if you agree that your wave function is proportional to spherical harmonic, that your function is eigenfunction, then you replace the action with a number. Okay, this was the kinetic energy. Minus beta over r. This is the potential energy of interaction, and parameter beta was equal to constant k, 1 over 4 pi epsilon naught. If you have a charge of nucleus Z E and charge of electron, this would be the constant of interaction. There's a combination of this, or just k. Or if you speak about hydrogen, Z equal 1. Yeah. So then I can replace L square now, and then I can cancel operator function y, because function y will be everywhere. These derivatives over r are acting only on the radial part. So this y spherical harmonic will be the same everywhere. Just cancel this. So then a short notation would be second derivatives from r plus 2 over r prime. There is a function y, but I cancel this. I want to cancel this, so I'm not going to even write it now. Then you have centrifugal potential. Then you have Coulomb interaction, so electrostatic potential. And then you have just eigenvalue for your Hamiltonian. Again, I could cancel y because one operator L square acting on the spherical harmonic, it does not change it. You just get this constant. So parameter L can be 0, 1, 2, 3, any integer number starting from 0 and positive. So L means the maximum possible Z component of angular momentum. So I believe we can start from this. Yeah? Maybe I'm gonna comment a little bit on centrifugal potential. or effective potential. So this part of kinetic energy related to angular motion. I'm sorry for this noise. So, but once you replace it with angular momentum, which is constant, then it becomes part of effective potential for radial motion. And depending on the value of angular momentum, your effective potential may look like this. So what we want to find, actually, we would like to find the possible energy levels in this potential, effective potential. So you're going to have ground state, first excited state, and so on. And you have to be careful because if you change angular momentum, you actually also change the effective potential energy because it knows what is your angular momentum. So you have some information inside this potential about angular momentum because that's why I call this effective. It's effective for radial motion. Okay, if you're ready, we can try to manage this situation. Apparently, it's a differential equation of second order. I have second derivatives, first derivatives, and I have three terms which proportional to r, and r is my radial part of the wave function. What can I do about it? I don't even know. Maybe I'm gonna just rewrite it. So I'm gonna start. Yeah? I have to be very careful because if I make a one small mistake, there will be no chance for me to recover. If you can check my calculations, that would be nice. This is radial kinetic energy. Then you have potential energy. So centrifugal potential, Coulomb interaction, and maybe I can bring energy to the right side, to the left side. Yeah. So I don't know this parameter energy. I would like to find this parameter E. So I would like to get this set of allowed energy levels. So quantization of energy levels. And of course I don't know R, the radial wave function. So we're gonna do the same what we did for simple harmonic motion. I'm gonna find asymptotic behavior, how my equation and how my solution behave at very large and at very small distances. And it's gonna take, I would say, about 1 hour to solve this equation. So try to bear with me a little bit. So first part, r goes to infinity. Let's look at this term inside these brackets. At a very, very large distances, which term will be most important? Out of these three?
E.
Only the energy, yeah.
Yeah.
Because energy is a constant, absolutely right. So, and this is 1 over r squared is gonna disappear or goes to 0. And potential energy of interaction also goes to 0. So then if I'm looking for asymptotic behavior, only this term will survive. So speaking about these two guys, I'm not really sure, but I would argue that 1 over small r prime, could be small as well. So I know that this is the correct answer, so I would just neglect this term as well. So my equation will look this form, this way. Or we can say our second derivatives would be equal to negative 2me h bar square r. So when you solve this equation, it's important to know that this coefficient 2me over h bar square, is it positive or negative? It depends on the energy. What kind of energy you are looking for, positive or negative? And this is why this graph can help you a little bit. The energy you are looking for, positive or negative?
Negative.
Negative. So if I pick a positive energy, you can do this, yeah? But this state would be unbound. The particle can go to infinity. That's possible. That would be kind of a scattering process, electron on a proton. But it's not a hydrogen atom, it's not a bound state. We're looking for negative energies. So negative energies are bound states. So then this coefficient would be positive. So I can write it explicitly like 2m absolute value of energy h bar square r, or maybe some call this k square. Because it's positive, I can call this k square r. So this asymptotics was not bad, yeah? Second derivatives equals k square r. What will be the solution for this? Exponent plus minus kr, yeah? Every time you take derivatives, constant k will go out. And if it's negative k, because you take second derivatives, minus k and minus k will give you k square. Which sign I have to pick, plus or minus? Remember, this is radial distribution. What sign corresponds to bound state?
Minus.
Minus.
Minus, yeah, because your wave function should decrease. If you cannot draw a wave function, so wave function should go down at large distances. It would be disaster if your wave function would grow. It would be hard to make interpretation of such solution. Okay, we had something similar to this before. It's not like a completely new situation. Okay, then now I can go back and justify that this term is small because I neglected this term. Just for myself. So r prime 2 over r would be negative 2k r and then exponent. And I see that this term is smaller than the second derivatives. Because this term is 1 over r, k over r, and this term is just k squared. So I didn't take this into account when I wrote this equation, and it was okay. So for asymptotic behavior at very large distances, this would be my wave function. So at very large distances, it goes down exponentially as minus kr, where constant k is the square root of 2m, we can say minus e, or you put absolute value e over h bar square. Remember, for example, simple harmonic motion, the wave function was proportional minus x squared. Like this, yeah, or not? So there was proportional minus x squared, not a linear function. This is linear. Okay, that was about 10% of the entire work, yeah? It wasn't that bad. The first part, r goes to infinity. What if I try to find asymptotic behavior when r goes to 0? So something very close to the origin. If r goes to 0, and I look at my effective potential energy and just energy, which term will be the most significant at small distances?
The first one.
Centrifugal potential, yeah? This is 1 over r squared. So then I can neglect Coulomb interaction and energy at very small distances. Speaking about these two, I'm not sure if I can neglect both of them, because if you have a polynomial function, taking derivatives is equivalent that you divide it by r. And then I can't really say which one will be greater or smaller. I'm going to keep both of them this time. So my equation will look like this then. It's actual Schrodinger equation, but without any potential and without energy. I can probably cancel out h bar square over 2m, yeah, in this limit. And then I have something nicer here. R prime prime plus 2 over r prime minus, because negative sign, l plus 1 over r square r. This is standard equation to some extent, because you have the same amount of derivatives and 1 over r. Let's say first one, you have two derivatives. Second one, you have one derivatives and 1 over r. The next one, no derivatives, but twice 1 over r squared. Fortunately for me and for you, this equation has a very simple and nice solution. The solution can be found as r in some power, because every time you take derivatives, you reduce power by 1. So the first one, you reduce it by 1 and one more time, by 2. The second term, you reduce it by 1 through the derivatives, but you also divide it by r. Again, you reduce it by 2 times. And the last one, you simply divide it by r squared. So this is a standard form for solution for this equation. Probably if you take or took differential equations, you know this. What I have to find is possible sigma. And this will give me the asymptotic behavior at very small distance. So I'm going to plug it in. And I'm going to just put equal sign, just because I want to plug it in. And my goal will be to find this asymptotic behavior at small distances. So if r is small r power sigma, then second derivatives would be sigma minus 1 r sigma minus 2 correct me if I'm wrong, then 2 over r prime would be equal what? Can you help me with this? You take derivatives, yes, you multiply it by 2 and you divide it by r. What you gonna get? Double sigma, I guess, yeah? Is it clear or not? Does it make sense?
Yes.
Yes. Okay.
Okay. So then my equation now, so I can just plug it in and I can see what kind of sigma should be for my asymptotic behavior. Second derivatives, sigma minus 1. Then the second part of the radial Laplacian. Then I have centrifugal potential minus L plus 1. And you have your radial wave function divided by r squared. You see how nice it is? I have the same r power sigma minus 2. And of course, it should be like this because it was my main point. When I noticed that this property of this equation, I already knew that I can find solution like this. So it's not something people don't know. Okay, then I have a quadratic equation for sigma now. Can I combine this together? Maybe just put it as it is. What will be the combination of these two? Sigma
Sigma square plus sigma.
square plus sigma must be equal L square plus L. What is the solution of this equation?
Sigma over L.
Exactly,
Oh no, equal to L. Yeah.
equal to L. But this is only one solution, yeah? This is quadratic equation. There should be two solutions. So this is sigma 1. What is the second solution for this equation? Let me write you the answer for this. So the second solution would be equal to minus 1 minus L. You can check it if you want. Maybe I can rewrite it in slightly other form, so it will be easier for you to check. Sigma plus 1, L plus 1. Apparently one solution would be sigma equals L. No problem. The second solution, let me plug minus 1 minus L or minus 1 plus L. So instead of sigma, I'm going to plug minus 1 plus L. And instead of sigma plus 1, this would be negative L. Because if you take sigma and add 1, you get minus L. I don't know if it's clear for you or not, but if you remove negative sign, you're gonna get L plus 1, yeah? And now it's a little bit non-trivial. Which of them I have to pick? R power L, so I have two asymptotic behaviors now. So my R can be proportional the radius in power L or 1 over R L plus 1. There is no real reason for wave function to go to infinity at r goes to 0. And between these two asymptotic behaviors, I would prefer this one, but not this one. Because this goes to infinity, and this infinite probability of finding particles at the center makes very little sense. In opposite, this one makes a lot of sense. So if L is non-zero, I don't know, L equal 1 or L equal 2 or L equal 3, then your radial wave function will go to 0 at small distances. Why does it make sense? It makes sense because of this centrifugal potential. Centrifugal potential does not let your particle to come very close to the center. The probability should decrease. You can't really find your particle very close at the center, or the probability should be small. And the higher angular momentum you have, the less probability you would have to find it close to the center. So, and the second asymptotic behavior doesn't give you this property. So let's say if you have okay, something like this. So in my opinion, it justifies this choice for this asymptotic behavior. And you can just remove from consideration the second asymptotic behavior because it's simply unphysical in this setup. I would say if you have angular momentum, non-zero angular momentum, then you shouldn't be able to come very close to the center, or probability to find close to the center should be small. Exception would be if you L equals 0. This means you don't have angular momentum. In this case, your R is a constant, and you have no problem coming to the center. But in this case, you don't have angular momentum, so then it would, your effective potential for L equals 0 will look like this. So there is no centrifugal potential. You can definitely reach the center. There is no problem with this. So L equals 0 is a little bit special. When you have a spherical state without angular momentum, you actually have a finite probability to reach the center, the nucleus. If you have a non-zero angular momentum, you have centrifugal potential which deflect you and does not let you to come very close. So I'm very satisfied with this asymptotic behavior, and I don't want to consider a second one. So the conclusion from both of this, that my radial function must have r power L asymptotic behavior at very small distances multiplied by exponential decay at very large distances. And now in between, I can have any function of R. And this would be the form in which I will try to find solution. So I'm gonna look for f as a polynomial function. The same what we did for simple harmonic motion. But if I want to keep it as a polynomial, I had to remove or separate the asymptotics. Due to centrifugal potential, and this is probability to go to the infinity, exponentially decreases. Now it will be real hard work because I have to write equation for the small f and substitute f as a polynomial and try to analyze this solution. It probably is the same amount of work as we did for simple harmonic motion. But I already spent almost half an hour and I didn't even start solving the Schrodinger equation. I was just working on the form in which I will try to solve Schrodinger equation. So let me remind you the Schrodinger equation then. Something like this, yeah? Centrifugal potential, radial kinetic energy, interaction, and energy. So this is the Schrodinger equation for hydrogen atom, the radial part of this Schrodinger equation. Now, my R is a combination of three different parts. So I would have to substitute it, and I would have to deal somehow with this Schrodinger equation. So definitely I'm gonna need your help. This is gonna be tough. So R prime. I need to calculate derivatives over R from this expression. Let me do this, but may I ask you to double check me, just in case. Well, the first derivative is from first part. Then the derivatives from f. Then derivatives from the exponent. Okay, I don't put here just f. Can you double check it? Is it okay or not? Okay, I believe it's fine. At least I don't see mistakes.
Yeah, it's fine, yeah.
Now, this gonna be the last effort, but it will take a while. The second derivatives. You can take derivatives from this one, but I'm gonna use a shortcut. If you have a, b second derivatives, it's a second derivatives, b, a, b second derivatives, and double a prime, b prime. So then something like this is a normal rule where you find second derivatives from a product of two functions. So what if you have three functions? Then you're gonna have a prime prime, b c, then a b prime prime c, then you have a b c prime prime, plus you're gonna have first derivatives and you have to double them. So let's say double a prime b prime c, yeah, or double a prime b c prime, or double a b c prime, or b prime c prime, yeah. I'm probably gonna go with this rule rather than taking derivatives from this one. Or maybe it's equivalent. It's up to you. In any case, you need a lot of patience and to be just accurate to take second derivatives from this R. So let's start. The second derivative is from R power L. L minus 1, R, L minus 2. It's a second derivative from this guy. Let me double check this separately. So first derivative gives me L, second L minus 1, okay, good. Plus, second derivative from F. This is easy, because I don't really have to do much, but it's going to be F prime prime. Second derivative from the exponent, minus K will go out twice, so it will be plus. Okay, these are three terms, corresponds to take second derivatives from the first, second, A, B, and C. Now you have cross terms, and we have three different cross terms. A and B, when you take derivatives from the first and the second, double L, R, L minus 1, F prime, exponent. Double derivatives from the first, from the second, exponent. Okay. Plus double from F and exponent. Actually, when you have exponent, you'll get negative sign. So it's going to be minus double K R power L F prime and exponent. That was from the exponent and from F. And minus double K from first and the last. K from the last, L, R, L minus 1 from the first, and this is the second. 6 terms. Wow. Then you have to add them. Let's try. But if I want to add them, I need to take R prime and multiply it by 2 over R. So I'm gonna just form this term. It will be easier for me to add them. So I'm gonna multiply it by 2 and divide it by R. First term multiplied by 2 divided by R. The second term multiplied by 2 divided by R. And the last term minus 2K R L minus 1 F and exponent. Complicated, yeah? So let's try to see what kind of terms do we have. Maybe we have some simplification or cancellations. For example, this term, let me find something similar to this term. Something I can combine with from here.
The first and the last one.
Maybe the first one, because the last one has K.
Yeah.
And the last one has a power which is different, yeah? This is L minus 1 and this is L minus 2. I can combine them. F is the same, exponent is the same, power is the same, L minus 1 plus 2L. Can I combine them? L, L minus 1, and 2L. What I'm gonna get if you combine them? You
Square,
can
square plus L.
L squared plus L. So I'm gonna write it as L, L plus 1, and then this guy, F, and exponent. Okay, thank you. F prime prime. This term is the only term like this, yes? I don't have any other terms like this, so there is nothing I can do about it. I can just write it. Absolutely. What else can I do? I have several terms which are like an F prime, and then couple of them would be
Yeah, the same. Yeah, 2L are L minus 1, and there's another one. Yeah, exactly.
and they both positive, yeah? Okay, can I combine these two guys? And I have another term, but this another term has different power, R power L, and this is L minus 1. So I can combine the green ones. What will be the coefficient? This is 2L coefficient, and this coefficient is just 2. So then when you add them, the coefficient would be
2L plus 1. 2L.
yeah,
2.
2L plus 1. Yeah, I got you, Amaru. Plus 2L plus 1, yeah? 2L plus 1, this power F prime exponent. It looks complicated, but actually what you need just to be very accurate with this. And you have to know what you're doing. Okay, what else do I have? Mm, this guy, and this one. Maybe these two.
Yeah.
It seems like I have again 2KL, and this is minus 2K. So then I can try to combine at least these guys. What I'm gonna get from these two?
Minus 2K.
L plus 1, yeah? Minus 2K L plus 1, then the power F and exponent. Okay, we are moving too slow, but hopefully we don't make mistakes. Minus 2K L plus 1 power F. Oh, two more terms, and we are good. This term, I don't want to do anything about it. I just want to write it as it is. K square, whatever. Finally, the last one. We don't have any terms like this, do we? Because this R power L. So let me just write it as it is. Then I don't want to do much about it. Minus 2K, minus 2K, R power L, F prime exponents. So this guy must be equal to what? So let me remind you the Schrodinger equation. Let me put everything to the right side now. You have minus centrifugal potential plus beta over R plus energy multiplied by R. So I'm gonna multiply it by 2m h bar square negative sign. So what I just found here must be equal to this right side. So and you don't have to do much about it. You can just plug R, which is R power L, F, and exponent. Just a multiplication. But the coefficient should be accurate. So the effective potential with negative sign, energy, and then this coefficient from the kinetic energy, from this, yeah, h bar square over 2m. So centrifugal potential, h bar square cancel out, 2m cancel out, negative sign cancel out. You're gonna get L plus 1, L plus 1 over R square multiplied by R power L F minus K. Then the last term would be negative. Okay, let me give it a little bit more space. The last term negative 2me h bar square energy 2m negative R power L F exponent, and the middle term would be negative 2m beta over h bar square R and this function. Okay, let's double check it. Centrifugal potential cancels out, R square, good. Energy term, energy minus 2m h bar square, function, it's good. The potential energy of interaction, negative 2m beta h bar square R. Okay, good. I don't know if you had time to check it, but it seems good. Now, I'm gonna simplify it a little bit more. For example, R power L over R square. I can replace it with R power L minus 2. That would be fair, yeah? This guy, I can replace with R power L minus 1. This one I can't do much about it. Oh. We have 6 terms on the left side and 3 on the right side. Actually, that was the most hard work. Starting from this point, the life will be easier. So we basically solve the problem. Let's try to simplify it. What can we notice? Can we notice some similar terms?
The first and the first one.
The first and the first. This came from centrifugal potential. They're supposed to cancel out each other. Do they cancel out each other? Yeah. They're supposed to cancel out each other because we pick right asymptotic behavior. So What else? I would say k squared term. Remember your k square was equal to minus 2m bar square. This k squared term and this one, they're also supposed to cancel out each other. And these cancellations are not coincidence. That's because we picked asymptotic behavior in a right way. What else can I do? I can try to combine different terms. For example, this term. Can I combine this with something? Maybe with this one, yes? R L minus 1 F exponent. They don't cancel out each other, but I can combine them into one term. Then F prime prime is gonna stay, and these two guys, maybe I can combine them as well, yeah? No, I can't. They have different powers. So then you have this goes away, these are combined in one, then you have 1, 2, 3, and 4. So after all this work, you're going to have only 4 terms. Can I cancel exponent, for example? Yeah? Oh, okay. What I'm going to get? This term cancel out, so I have this one. So I have r power L F prime prime, yeah? This one, okay, plus 2L plus 1 F prime. Green one. Let me bring this one to the left now. So I'm gonna have plus 2m beta h bar square minus 2k l plus 1. So I'm trying to combine these two guys. R L minus 1 F. So I got this one, I got this one. I've got this guy, green ones. This cancelled out. So I have only last term. Yeah, maybe I can combine this as well. Can I maybe simplify it more a little bit? What can I do? R power L? Can I get rid of R power L? This would be 1 over R,
Yeah.
and this is going to be 1 over R. But I'm not going to have here and here anything. So maybe it will make my equation look nicer. So F prime prime. Then let me combine these two guys together. Plus 2L plus 1 over R minus 2K F prime. So these two guys. after I cancel r power L. And this constant, I don't know, maybe I can give it a name to this constant, like lambda, if you want, just to label this as something. So plus lambda over r f equals to 0. So this is the definition of my lambda. I cannot label this as another constant because there is a power of 1 over r. But this is just a constant. And this constant, you have angular momentum, you have the mass of the particle, the constant of interaction, h bar square, and constant k. And constant k, remember about energy. So because it's a square root of 2m e over h bar square, so this energy is here. And also energy is somewhere here. Let me double check. I'm a little bit worried about this 2k term. I don't see how it can appear. Let me double check if this 2k f prime actually happens in this. Where it came from? It came from
The last term, no, yeah, the last term and the first.
here, yeah? It came from this one. So when I took derivatives from exponent and from f prime, and it was double because it's a second derivatives. No, it should be there. Okay, I understand the origin of this term. No problem. So this term came from where? This term came from this one. You take derivatives from r power L and f prime. Yes, I would agree with this. So you must have something like this. This is obvious term, and now this one to double check it. How can I explain this? Basically, it came from these two guys. The constant of interaction, beta, it was beta over r, so that's why I have this one. And this is came from derivatives from this and from this, double. Okay, I'm satisfied. I'm sorry for this long checking because I don't really want to make mistakes. Maybe to make it even more simple, I'm gonna just multiply it by r. So then it will be even nicer. So r f prime prime plus 2l plus 1 minus double kr f prime minus double kr and plus lambda f. Okay, I believe this is the most simple form we can ever wish. So constant k was minus 2me h bar square. Constant lambda was 2m beta over h bar square. Minus double k l plus 1. Okay, done. Then let's try to play around. So then we completed the most complicated step. We wrote equation for this polynomial function. Remember, your R was asymptotic at small distances, asymptotic at large distances, and some function f in between. So then if your R satisfies Schrodinger equation with correct asymptotic behaviors, then function f must satisfy this equation. And this is my Schrodinger equation in a strange form, but it is Schrodinger equation. We have to complete the very last step. We're gonna write f as a polynomial, and we will do the same what we did for simple harmonic motion. We will try to cut this polynomial. So my function f would be some constant c0 plus c1r plus c2r square plus c3r cube and so on. So something I can write as a summation over n from 0 to infinity. Well, this shouldn't be infinity, yeah? I would expect you have some cutoff maximum number when you want to stop, because if polynomial will go to infinity, it will start to grow exponentially and it will screw up the correct asymptotic behavior. So I would expect something like finite polynomial Cn r power n. So then not at all energies the series will stop. Only at some very magical and specific energies you can stop this polynomial at some upper limit. And this will give me the allowed energies for my hydrogen atom. Let's keep this in mind. Let's calculate the first part. You take second derivatives and you multiply it by r. The first term will go to 0. Second derivative from c1r. I guess it's also 0, yeah? Because the first derivative is 1 and second is 0. What about this guy? Double c2 r. When you take second derivatives, it's going to be just 2, but then you multiply it by r. Is it correct?
Mm.
What about this guy? Second derivatives and then multiplied by r. 3, 2, c3. What will be the power?
I think 2C2 should be without R, right? And this term.
Yeah, but then okay.
Oh, okay, okay. So
But
it's
then
R.
I want
yes.
to multiply it by r because this is what I have in my
Oh,
equation.
okay.
Yeah, you're right. So,
It's R, yeah.
one way to do this is just calculate second derivatives and then multiply it by r after you calculate it. In this case, you're right. There is no r and this power 1. What will be the general term? Cn r power n. Gonna be
Times n minus 1.
Cn r n minus 2. Yeah.
Right, yes.
Now, if I want to multiply it by r, now this would be r square, and the general term would be
Minus 1.
minus 1. Yeah. So, okay, this one is good. I would say f prime r is similar to f. I would like to combine them into one. But this one would be slightly different, so let's write this separately. So this is just f prime. So my f prime, let's calculate f prime. 0, C1, yeah. Then actually I may need some space here on the left. 0, C1 plus 2C2 R plus 3C3 R square plus so on. The general term for f prime would be n Cn, yeah, R n minus 1, yeah. And all this I have to multiply it by 2 L plus 1. So what I can notice that they are very similar. This guy and this guy. Yeah, look at this. C2R, C2R, C3R square, C3R square, Cn R power n minus 1, Cn R. So they actually look very similar to each other. I have to add them, so, and I would like to add them, and they have the same structure to me. Can we guess what would be the general term for these two guys? The general term. It's gonna be n minus 1, yeah. This is the same. Then you're gonna have plus 2L plus 1. Cn R power n minus 1. Would you agree? So if I combine these two guys, I have this, and then you have summation from n equals 0 to whatever. This is very nice. They have the same power in front of the same coefficient. Did I forget n here?
Yeah.
Yeah, my bad, sorry. You should check me. You see how complicated is this? One small mistake, and that's it.
And this,
Even I can put n
yeah, it was also-
outside. Okay, let's do this because I believe it may look nicer. And then what will be inside the brackets? It's going to be n minus 1 plus 2L plus 2. So I can simplify it even more, yes? N minus 1 plus 2 is plus 1. Very nice, yeah? At least I have some not very scary, nice expression for this. Then let's talk about these blue terms. Apparently lambda f is trivial, you just multiply it by lambda. So you have to work a little bit with this minus 2kr f prime. I have to take derivatives, and we already did derivatives once, and then you multiply, so this is the derivatives, yes, basically. But then you multiply it by r, and the coefficient minus 2k. So it's going to be minus 2k multiplied by, so when you take derivatives, get 0 from C0, then from C1, get C1, and you multiply it by r, plus 2C2 r squared, plus 3C3, and so on. What will be the general term for this? N,
Cn,
Cn, and what power?
Rn,
N, yeah? And then you have lambda f, the last term, lambda f. It's going to be lambda multiplied by C0, C1r, C2r squared, and so on, Cnrn. Okay, if I combine them, what will be the general term?
n plus 1,
Where did you get n plus 1? Say it again, Amaro.
is we have NCN on top and they have CN on the bottom.
But this n comes with this coefficient, yeah?
Oh, I forgot.
So you would say minus 2kn, Cn r power n, and plus lambda, yeah? So this is not bad. The last two terms, they combined into this one, and then you have this one. So now you have to compare coefficient in front of r power n. So r power n, you have a coefficient Cn lambda minus 2kn must be 0. And if you want to have r power n, this should be n, c should be n plus 1, yes? Because how can you get n power n? You have to consider a next term to get the same power. What I'm trying to say, let me show you an example. Let me pick power n equal 1. So this is going to be these two guys. But from blue terms, r power 1 is this one. So if I combine them, I mean, I would say I would have something like minus 2k lambda 1 c1 power r, and from these two guys I would have 2c2 plus 2l plus 1, yeah? And this would be C2 and the same power R. And they should be 0 because this F should satisfy this equation, and it must be 0. for each power. So then if you compare power r equal 1, you would see that C2 can be related to C1. I'm trying to write it for a general term for r power n. So for the last two terms, I just have r power n. So I have a Cn, Cn, r power n, and this coefficient here. What about here? This part. How can you get power r power n? This n should be n plus 1. Yeah, you have to take next term. Would it be obvious? Then you have to say Cn plus 1. Then that would be r power n. Cn plus 1 power n. And here I would have n plus 1, n plus 2, and 2l. N plus 1, n plus 2, and 2l. N plus 1, n plus 1, 2l, Cn plus 1, r power n. So they should be 0. Cool. So it means that I can relate next coefficient to previous coefficients. I have this recursion relations as we had for simple harmonic motion. Does it make sense? This is a solution. Once I know coefficient C naught, I can find C1. Once you know C1, you can find C2. If you know C2, you can find C3. At this condition, between coefficients, your function f will satisfy this equation. And if function f will satisfy this equation, that means your radial wave function will satisfy the radial Schrodinger equation. This is the solution for f. Congratulations, we just solved the problem. Now, how can I get energy? What would be the criteria? So your R is like this. Your function f is like this. And so on. And your coefficients, they can be related to each other. So the next one to the previous one, it's kind of recursion relations. N plus 1, n plus 2, plus 2l. Lambda minus 2k n. Lambda minus 2kn. Okay. how can I get eigenvalues, the energy? Remember what we did for simple harmonic motion. What was the main procedure? What did I say?
So the energy has to be negative.
The energy is negative, yeah, but right now energy is going inside k constant and inside lambda. And it seems like energy can be any. But we know that we should have only allowed values for energy.
So lambda minus 2kn equal to 0.
Absolutely.
Yeah.
Then you have to pick energy in such a way that at some point the numerator will be 0. Then, for example, if I pick lambda equal 2k, just for example, yeah, then for n equal 1, you're not going to have next coefficient. Because if lambda by chance equals to k, then once you start to calculate from C1, you want to calculate C2, you're not going to be able to do this, you're going to get 0. And that would mean that all other coefficients would be 0. What if lambda would be equal, let's pick n equal to 4k, then which coefficient will be 0? If n equal 2, and then you will try to calculate C3, yeah? Then C3 will be 0, and then starting from C3, all the coefficients will be 0. What if lambda equal next one, 6k? Which coefficient will be 0?
C4.
C4, and so on. So if I have such freedom that I can pick energy, any energy I would like, I can control how many non-zero coefficients I have in my function f. I can start with even lambda equal 0 maybe, yeah? It should be in front, but if I pick lambda equals 0, then n equals 0, it's already C1 is 0. So then you have only C naught non-zero. So depending on this lambda, you can cut this polynomial. You can make it a certain power. And the power of polynomial would correspond to what kind of lambda you picked. If lambda is not one of these magic numbers, then the series will continue to infinity. And most likely your asymptotic behavior will become wrong. And it's not going to be a good solution. So this is a moment of a little bit of magic when you can define all possible energies, when you have quantization of energies. When you say that this polynomial should be finite, I should be able to cut it. But for arbitrary energies, for arbitrary lambda, you cannot cut it. You can cut it only for very specific lambda. So for this specific lambda, which corresponds to specific energies, you're gonna have a normal solution which makes sense. Some asymptotic at r equals 0, asymptotics at infinite distances, and a finite polynomial. So then the quantization of energy, of course, comes from Schrodinger Equation. But technically it comes at this moment when you want to stop this function f from being infinite in terms of these powers. And of course, it's very important to get this recursion relationship in a correct way. And I don't know, I hope I got it in the correct way. Maybe last time when I was calculating this equation, it was maybe 20 years ago. No, not 20, 15 years ago. I am absolutely not sure that I did not make any mistake, but we will see right now. Yeah, it's very easy to check. So then, quantization of energy. Quantization of energy. When lambda must be equal integer number multiplied by 2k, 2kn. And n can be equal to 0, which means lambda equals 0, or 1, or 2, or 3, or 4, and so on. And you can put some small n here, like a subscript, just to distinguish that you have a different set of lambdas which corresponds to different polynomials and different values. Okay, what was the lambda? Do you remember? Lambda was equal to 2m beta over h bar square. I don't remember. Was it like minus 2k? I doubt. Let's go back and check. I should have written, okay, this is lambda. 2m beta, okay, minus 2k and lambda plus 1, yeah? Remember? There was a label, convenient label for all of this happiness. So L plus 1. So the quantization will be like this now. 2m beta h bar square minus 2k L plus 1 equals to 2k and some value n. The value n would be the power of the maximum power in the polynomial f. It's important. So if my n equals 0, then your polynomial just a constant. If my n equal 1, then it would be a linear function of r. And if n equal 2, then polynomial f will be a quadratic function and so on. So n is basically the power of your polynomial. Okay, in this equation, what is my energy? My energy is inside constant k, yeah? So if I want to find energy, I want to find constant k, and from k, I can find energy. So let's find k then, yeah? This is already quantization rule. So 2k n plus L plus 1, is it correct? If I combine this, n L plus 1, okay, must be equal to double 2m beta over h bar square. So my constant 2 goes away, yeah? Constant 2 goes away. So then k will be equal m beta square over h bar square n plus L plus 1. Is it correct?
Beta square?
Uh,
Oh,
yes. There is no square, yeah? It was just 2m beta. Thank you.
yeah.
It was 2m beta and I cancel factor 2. Now my constant k, if you remember, it was the square root of minus 2me over h bar square. So I can make it square and then find energy. Minus 2me h bar square would be equal m square beta square h bar power 4 n plus L plus 1 square. By the way, this n plus L plus 1, it's an integer number which can start from 0 when both of them are 0. Let's call this capital N. It will be more convenient for me. It's called principal quantum number. So then this would be just this big principal quantum number. It's an integer because my n is integer starting from 0 and so on. And angular momentum L, it also can be 0. So this n will start from 1 because of this 1. I can have this principal quantum number to be equal to 0 because of this 1. So what can I do? 1m goes away, h bar square, and factor 2 should go here. So the energy would be equal negative m beta square over 2 h bar square n square, where n equal radial quantum number, the small n, plus angular quantum number plus 1. I believe you already can recognize it, yeah? Does it look familiar to you? This is a correct spectrum of hydrogen atom. The spectrum is 1 over n squared. Let's calculate this quantity, m beta square over 2h bar square, because it's a very famous constant. So m beta square over 2h bar square. I may need your help because I'll need a calculator. If you have a calculator, so just help me. So then beta was constant k z e square, and I'm gonna take z equal 1. So let's talk about hydrogen. So then just a constant k and e square, so you have to make it square. Okay, and this is what I call Rydberg constant. The mass of electron, k e square square twice h bar square. If I plug all the numbers and be very accurate, I should get a value which we all know and appreciate. But let's do this at least once. Actually, there is a better way of doing this. I may want to teach you another way. I'm gonna calculate it like this. I'm gonna multiply it by speed of light square and divide it by speed of light square. I don't know if you can see this or not. This is mass of the electron, this is speed of light square, this factor 2. Then h bar c, when you make it square, c square will go away and h bar square will stay. And this is a constant of interaction. So probably you can believe me on this, that this combination has no units, because mc square is already units of energy. And I'm calculating energy, so this is already energy. So this combination should have no units. This is called fine structure constant. And there is a special label for this alpha. And this alpha is approximately 1 over 137. It's called fine structure constant. So it will help me to calculate this Rydberg constant relatively fast, because this is alpha square. Then mc square, this is the rest energy of electron. The rest energy of electron is 0.5 mega electron volt. I just know this, and you can double check it if you want, but it will give me a faster way to calculate in the Rydberg constant. So then the Rydberg constant would be half 10 to power 6 electron volts here over 2 multiplied by the fine structure constant square. Okay, this is where I need your help. Can you help me to calculate this? Can you take half 10 to million, half of million, divided by 137 twice and divided by 2? How much you gonna get?
I got 13.32.
Okay, then if I would be more accurate with the electron mass, then you will get 13.6. And the units are
Yes.
electron volts, so not joules, electron volts, because this was mega electron volts. It's units to measure energy. So and I was talking about the rest energy. This is a very famous Rydberg constant. So then coming back to my quantization of energy, I have this Rydberg constant here. So the quantization of energy in a hydrogen atom would be negative this Rydberg over n square. If you have z not equal 1, then you have to plug z here, because constant beta was with factor z, and z will be square. So then z square. Yeah. So if you speak about simple hydrogen like z equal 1, then the ground state energy would be minus Rydberg. Then the next excited level would be minus Rydberg over 4. Next excited level minus Rydberg over 9. So you have a spectrum of your hydrogen atom. Schematically, the potential, and then the ground state energy would be minus Rydberg. Then the next one would be minus Rydberg over 4, and then next one minus Rydberg over 9. And actually, more higher levels will be more dense here when you go to 0, close to 0. So n equal 1, it's only possible, let's write it, as a radial quantum number plus angular quantum number plus 1. How can you make n equal 1? It's only n equals 0 and L equals 0, yeah? So the ground state, you can make it 1 only if both n and L are 0. So this is only S state. How can you make n equal 2? What kind of possibilities you have? N equal 2.
And 1 equals 0.
N1 L equals 0, or you have another option. Can you make N equals 0 but L equal 1?
No, you cannot.
Why?
Because L goes from sorry.
L is not restricted. L can be from 0 to 1 to 3 to infinity. So L equals 0. What kind of state it is? S, P, or what state?
Yes.
S state. L equal 1, P state, yeah?
Yes.
This is your second shell. This is a S shell and this is another level shell. What about N equal 3? What kind of options you have for N equal 3?
You have SPD.
You have a N equal 1, L should be equal to, oh, N equals 0,
Yeah.
L should be
So
2. What else can you do?
1 and 1.
1 and 1. And what else?
1 and 0.
You mean 2, 0.
Yeah.
So you have a S, P,
D.
SPD. So when people in chemistry, they occupy levels. Now, if you recall a little bit of chemistry, these are the levels which you can occupy. So you have a little bit degeneracy when you have the same energy for S and P, and D. But actually, there are different corrections to your Coulomb interaction which can split this energy. So S level and P level may have different energies at the very end. But if you have a pure Coulomb interaction, they have the same energy. There's Rydberg minus 4, Rydberg minus 9. So if you're talking about a realistic hydrogen atom, so N equal 1 is a pure S state, N equal 2, you may have a splitting into 2, S and P. But there should be some interaction which will split these two. Because originally, for pure Coulomb interaction, you have the same level, the same energy. So N equal 3 splits even more. And then you start to occupy these levels with electrons to form an atom. And of course, unfortunately, we don't have time to discuss Pauli principle and how you occupy levels and what happens if you complete levels and what is the spin of electron and how spin is important. I would just want to emphasize the result of these calculations. So the energy, the quantization of energy in a hydrogen-like atom will be negative some constant which is 13.6 electron volts z square n square. This is very nice actually. This is, I don't know, you see how much work we did. Then at the very end, we confirm the experimental result because this energy can be measured when electron jump from one level to another level. Let's say electron get excited and jump to N equal 2 or n equal 3. And then it jumps down to n equal 2. So the difference between energies will be emitted as a light. So this light will have frequency as En1 minus En2. So when you jump from initial level to final level, this is the amount of energy you release, and this is the frequency of the photon. So the wavelength or frequency can be measured. And if you know these frequencies, you can measure the difference between energy levels. And you know the story very well because I started from that story, that it was, people don't know why, but these frequencies, they obey very strange law, yeah, like this. So something like some constant 1 over n squared minus 1 over m squared, where this guy has some integer values. So this was discovered way before quantum mechanics was developed. And there was no any explanation why this should be difference between integer numbers, 1 over squares of integer numbers. So we just derive it. And after doing this, you start to build certain trust into quantum mechanics. And Schrodinger equation is an equation which adequate describes this, your nature in an adequate way. Okay.
Great.
And you see how much work it was for us, yeah? And I try to go fast through this. And I believe we should finish at this point. I know I did not talk about many things I promised. And then it would be interesting to talk about identical particles and bosons versus fermions and quantum gases, like Fermi gas. And Fermi gas, you can talk about, for example, neutron stars. So, of course, we did not talk about spin. Many topics, but we spent good 20 hours, yeah, talking about quantum mechanics. Okay, just thank you.
So there will there be a second part
Second part
with all those topics that you mentioned
next semester.
next semester?